Geometry, geometry. We should have more geometry carols. Okay, this is about chapter 12. Oh, there we go. There's your questions. Why not? This is about chapter 12, which is about three-dimensional stuff. Put on your 3D glasses, because I'm coming at you. All right. Your do now next time is going to start with these questions about surface area and volume. So have a look at those. You'll be expected to ask those, lest ye be embarrassed by your peers for not knowing. Okay, so pause, read. Whoops. Sorry, come back to that. All right, the notes. So we're talking about 3D space now. First time we've ever done that. So you need some basic terms about what we mean technically by volume and surface area and that kind of stuff. I don't think any of this is incredibly new. I think you've heard about volume and surface area before. My daughter in 5th grade just learned the volume formula for a volume of a pyramid, so you've probably seen that kind of stuff before. Volume is a measure of 3D space, so we're going to be talking about stuff like cubic inches and cubic centimeters. So get ready for that. However, with a 3D shape, you have the outside, the inside space that's still measured up with, cubic units that you can like fill with something. And why does that little thing keep following me? And surface area, which is really the measure of the shape on the outside of a figure. So that's still a 2D measurement. It's like we're talking about how much stuff can you put in it for volume, but surface area is more like how much wrapping paper does it take to cover it. And by that, really the only way to do surface area is to think about some books call it a net, or a like making a box and unfolding it and finding the flat area of that box, so like all the covering space it would take to cover that up. Our book, and lots of books, divides up surface area, particularly of prisms, into these two categories. Before I get to that, let me tell you what we mean by a prism. Prism is a three-dimensional shape. I'm pretty good at drawing them by now. Three-dimensional shape that has I could get really crazy. No, I won't. Usually a top and a bottom. Has these two surfaces that are parallel and congruent. So I have this. I tried to draw a triangle one here. I have a triangle up here. I don't know. It looks like it might be equilateral. I'm not sure. And there's a triangle kind of down here on the floor. And those are supposed to be parallel. They live in parallel planes. And then in between those, I'm connecting the edge in this parallel plane with this edge by a rectangular face. And when you do that, when you have congruent plane regions in two parallel planes, there's a plane up here and there's a plane down here, and these regions are the same, and it's all connected with all the stuff in between it, then that's what we know as a prism. Prisms can be pentagons. They're harder to draw, but you can have a pentagonal prism. There's one in the notes. It looks kind of nice. You'll get better at drawing these after you do a bunch of times. You can have really wacky ones. There's one of those. I just have to draw the same shape down here. So impress you with my drawing skills. This is a really, really weird one. But you can kind of have, you can see what I mean here. Looks like this curtain kind of wall. This looks like it might be the shape of a water in a really funky swimming pool. As long as the shape down here is parallel and congruent to the shape of here, I would think of that as a prism. This one would be really hard to find any measurements about because it's so bizarre. But you could have a circle, perhaps. Now, some people call this a cylinder. Our book calls this a cylinder, and that's perfectly fine. But I want us to think of that as the category of prisms as well. The book separates out prisms and cylinders into two different sections. That's why I have 12.1 here and 12.3. I called it 3A. They have cylinders and cones in this section 3. I think if we do cylinders on the day we do prisms and we do cones on the day we do pyramids, we'll take care of two sections in 3 days. So we're doing the first half of 12.3 also. Makes sense? All right, so when we go to find the surface area of stuff like this, what the book does, or what the one approach is on this is, well, we have to add up all this stuff at once. Let's talk about just one of those shapes, like excuse me. Let's do a triangle one. The triangle one was good because what's nice about the triangle is that the walls, and I keep saying this in the notes too, the wall shape and the floor and ceiling shape are different. Here, the floor and ceiling, these things we want to call bases, the parts that are congruent and parallel, so this triangle up here, and I'm dotting this because it's kind of behind the wall here a bit, those we call the base. A base there and have a base here. I like to think of that as like the floor and ceiling, and then I call these things, and there's three of them. I don't know if you can tell there's three here, but each side of the ceiling or each side of the floor is going to mean that there's going to be a wall coming up from that. So there's three of these sides, these three rectangle faces. Altogether, we call the lateral surface. Lateral is another word for sideways. The collective, all the walls kind of stuff, that stands for, that's what lateral, they mean by lateral. And they have a formula for that. They call it LA. Lateral area technically is just going to be like these three rectangles added up. Actually, let's take this thing apart a bit. If I take this thing apart, I'm going to have a triangle on top. If I kind of unzip the corners, there's a rectangle. This front rectangle connects the top to the bottom. I'm going to unzip that this way. And then the wall in the back over there is going to come out over this way, and the wall on this side over this way is going to come this way. And that's the whole thing. This edge matches up with this edge, sort of, and different color. This edge is going to match up with this edge, and different stuff on the bottom. This edge is going to match up with this edge, and this edge is going to match up with this edge, and this edge, when you put it all back together, is going to match up with that edge when it wraps around the back. The other edges I didn't even have to cut. All right, anyway, this stuff in here, all of this, these three rectangles all together, which on the original was that sort of band that goes around the middle, that's what's known as lateral area altogether. And it's really easy to find all that together, because on all of these, when you unzip them, whether we had a pentagon or a square or a circle even at the top, when you sort of crack open the lid and the floor and unwrap the whole box, this middle section, the walls all together are going to unwrap and make a big rectangle. And that rectangle is going to have the same height as the prism, and then this length from here to here, this distance here, if you think about it, this is an unrolled version of the perimeter. So this whole rectangle, big rectangle is going to have one dimension's perimeter, the other is going to be the height of the prism. So there you go. That's a laugh. So that's just the lateral area of the prism. If I wanted to know the total area, they used TA in our book. I think most books use SA for surface area. Our book used total area. You have to take the lateral area, and then you have to add on some stuff. We didn't talk about this and this. If it's a prism, there's always going to be two of these bases. Always two of them. So for a prism, you can say add on two bases, and you'll have the whole surface area. If you took the lateral area and add two bases, that's everything. And the bases are always congruent, so it's always 2 times that same thing. And base could be different no matter what it is. If it's a triangle, you got to figure out how to find the area of a triangle. If it's a circle, find a circle. If it's a square, you got to find the square. So specific to each one is slightly different, because finding a perimeter of a triangle is slightly different than finding a perimeter of a square. But it's the same concept. We want the perimeter of that thing. It's that whole entire perimeter times the height. That will give us all 3 rectangles at once, all of the walls together at the same time, plus those, times the height, give it a rectangle, plus those 2 bases, and that's everything. The volume of that whole thing is, and again, you've heard this before, it's the area of the base. So like find the area of like one of these triangular post-it notes times the height. So we have area of the base times the height. And area of the base, I don't just mean one length, I mean area of a base. That's an area formula. And you notice in our book, and lots of books do this too, that they use a capital B here. That's different than when they used base as a small b. That's something else. That's just a length. This actually is an area. This capital B they use capitals because there was probably another formula used to get to this point. So this B stands for the result of another area formula. Here, it have to be area of a triangle. It'd be the same if it was area of a circle or area of a pentagon or a square or whatever you've got. So, and I said post-it notes. If you think about this, and we found the area of that entire post-it, if I multiply that by the height, it's like stacking those all up and I'm filling it up. Whereas lateral area, you can almost kind of think of, we were taking that perimeter. If I think about this perimeter here, it was like we had a wire frame around here. Multiplying that by the height is like taking that and coating the edges with it. Coating these, by edges I mean walls now. Coating the walls with a bunch of those wire frames when I multiplied it by the height. This is different. I want all of the space inside the whole base times the height, not just the ring around the outside. And that's pretty much it. You got lateral area, you got total surface area, and you have volume of these kinds of things, and cylinders. I keep saying floor and ceiling. I think it might be a little bit misleading, especially when the thing is sitting on a. Now this one's actually sitting on a lateral face. Remember, the definition of base is that those things have to be the parallel congruent pieces, whether it's facing this way or standing on the hexagon or whatever. This one is really confusing because I could actually call any one of those faces the base. The one it's sitting on now, I could call that the base, and this thing the ceiling, and call those all these other rectangles the lateral edges and the lateral faces. But the way they have it highlighted here, they're saying no, that's the base, and this is another base, and then the long ones that go around the middle, that's kind of the lateral. That's okay. Rectangular prism will do that. Pentagonal, you kind of have to say, well, the pentagons would be the congruent opposite parts. These other rectangles have to make the lateral area. Same thing with hexagon. I couldn't say that this rectangle is the base and the rectangle it's sitting on is another base, because those are not being connected by straight up and down rectangles. You have to have the two congruent opposite ones, and just so like all the points of the translation in between, and that's it, to call those the bases. Altitude is defined as the distance from the top to bottom. It's like the perpendicular distance between those planes. This can get really yucky if you're talking about something that's not straight up and down. We could actually have, let me make because it'd be easier to draw. Let me make a rectangle one. So there's a rectangle here, and there's a congruent rectangle in another plane, but it's not directly below it. Say it's more like over here. And you could have these planes being connected by edges like this, so the whole thing kind of leans over. Now that's just rude, and there's still a height which goes straight up and down, and it's perpendicular to those two planes. If the whole thing leans over, then now some of these faces are not rectangles anymore. That definition we had about lateral area equals perimeter times height, that doesn't work here. That only works for right prisms only. This is not a right prism. This thing, the leaning tower of prism, is called a oblique. And this would be oblique rectangular, but oblique prisms in general like this, you can have oblique cylinders. Those are really annoying. You have a circle up here and a circle down here, and connect that all together. It seems like it ought to be easy to deal with, but it's really not. The lateral surface on that is not a rectangle. It's some really funky shape. You never see these in real life, so it's like really obscure. Anyway, we'll deal with those when we have to. The volume is fine. You can still find the volume by taking area of the base times the height, but surface area is totally weird. So let me just explain the notes here. I say total area always equals, of a prism or a cylinder, always equals lateral area plus two bases, and I'm just saying what everything stands for here. Yes, B is the area of one base, but notice I need two of them in the total area. When we get to pyramids, of course, we're only going to want one base, so this stuff does eventually change. There's the prism area volume formula. Here's a better picture of a cylinder unwrapped. If you cut open the side of a can and flatten it out, yes, you're going to get a rectangle. And if you think about that, this edge, as it unfolds, is just going to become a straight edge of that rectangle, and it's going to have the same length as the circumference of the circle. It was formerly wrapped around that circle, so that's how long that is. It's one circumference, and of course the height's still the same as the height of the can. So here's your whole surface area laid out. It's two bases, there you see them, plus the lateral area, and the lateral area is just a rectangle that's circumference by height. So that stuff is in here too. The formulas for lateral area and volume. Volume, again, is just base times height, and really lateral area is perimeter times height, but perimeter now you can think of as circumference of this base. So this is all really straightforward stuff. Of course, you start getting into the problems, and things start to get like, whoa, I thought this was going to be easy, but kind of like we all thought at the beginning of the area chapter. But no, it's not always going to be that easy. However, there's really nothing else I can teach you in the way of rules. These are all the rules involved in these two sections. Well, all of 12.1 and then half of 12.3. The rest of it's just applying them in really funky situations where they cut stuff up and that kind of thing, which is why we do the video this way, and then we'll get together and we'll do the harder questions together in class on Friday. See you then.